talking about from before. No, there are people who didn't do the first reading. There's levels, my friend, of laziness. Okay? You know, there's... Come on now. I'm not that cruel. So, to do the questions? Yeah, the questions are really important because they're going to tell you how much you're comprehending. All right, so where did we leave off in class? Anyone? We went through Pear Deck, right? All right, and if I'm correct, we had finished Pear Deck, and we're on to weight. All right. Actually, you know what? Let me bring up a Pear Deck question that I felt I totally inadequately addressed. And it was, you know, you can always tell when a teacher making something up and pulling a fast one on you. Because that's exactly what I did then. I pulled a fast one, all right? Because I went and I gave an explanation for this problem, and I realized right in the middle of my explanation that my explanation wasn't adequate. And I was like, so you see? All right, let's move on. So let me actually address it. So it was this problem. It was the Ferrari that goes 25 meters in the first 4 seconds, and then in the second 4 seconds, so then it says how far will it go in 8 seconds. And the explanation I gave was inadequate. So let me actually give you a formal explanation for this. Well, the verbal explanation was solid. In other words, the average velocity in the first 4 seconds is going to exceed the average velocity in the second 4. Therefore, it can't go as far in the second 4 seconds as it did in the first 4. But since it went somewhere, it's going to be greater than 25 and less than double that. But the formal explanation is this. If I go and I break this up into 2 segments, this is going to be T1, this is going to be T2, and these 2 are equal. In other words, T1 equals T2, and both of them I'll call T. The initial velocity going into the first 4 seconds is VI1, and the initial velocity going into the second 4 seconds is VI2. Right? What can we say about VI1 and VI2? Okay, and what in particular, which is greater? That's right, or at least the magnitude of VI1. If we call this the positive direction, we can say that VI1 is greater than VI2. So now we write down the first kinematic equation for each. And what does it say? It says delta x1 is equal to VI1 t plus 1/2 a t squared. And then the second one says delta x2 equals VI2t plus 1/2 a t squared. And notice the t's are the same, the a's are the same. So what am I going to do? I'll subtract the bottom from the top. So let's subtract these two. What do you get? Yes. So, notice what happens to the 1/2 AT squareds? They drop. And so this is equal to VI1 minus VI2 times T. What can you say about this? VI1 minus VI2. What can you say about that? That this has got to be greater than 0. Why is that greater than 0? Because VI1 exceeds VI2. So therefore, we have delta x1 minus delta x2 is greater than 0. What does that imply? This implies that delta x1 exceeds delta x2. Or in other words, the maximum value, if I put greater than or equal to signs everywhere, the maximum value of delta x2 is delta x1. So in other words, this thing is going to go between delta x1 and 2 delta x1. So that's the formal explanation. So I went and I introduced you guys to weight. And I said, all right, weight is formally defined as, so Fg is formally defined as m times g. And which m is this? It's the gravitational mass. And then if I'm correct, I went and I said, all right, let me derive this. Did I do that? And how did I derive this? I put an egg in free fall. What are the forces acting on this egg? Gravity, right? Which is acting which direction? Down. And then what do? That free body diagram you put in to Newton's second law. Which side Newton's second law? To the left side. You have net F equals ma. Right? What's the net force? Negative Fg. Why is it negative? Because down is negative. And that's equal to m times a. But what's a for a body in free fall? That's right. And so you get Fg equals mg. And so now the question is, did I pull a fast one on you? And the answer is, yes, I did. Talk about with each other. Where did I pull a fast one on you? The question is, there's a reason why these two are not identical. It's very subtle. I think Chris has a hint. What is it? The other is the gravitational mass. So which one's the inertial mass? That's right. This right here is the inertial mass. So in other words, this whole formalism, what did I accept as basically as a postulate? That's right. I accepted as a postulate that m sub g equals m sub I. And what I want to express to you guys is this. For the purpose of problem solving, we're going to consider the two equal. But when we get to labs, you need to be a little bit more careful. Because how you measure one is different than how you measure another. And so then I went into, how do you measure one's weight? So how do you measure one's weight? What's the process by which I want to go measure my weight? Naturally, I go and step on a scale. And the scale does what? What does it measure? Really? So what does that mean? It's measuring the normal force. In other words, it's measuring the force that the bottom of my feet are applying to the scale. So the scale is measuring the amount of force that I'm applying to the scale. Or, put it succinctly, it measures the normal force. Well, so let's check this out. So naturally, Khalil goes and he carries a scale with him. And that scale's on the ground, and he stands on the scale. Okay? All right. So now, so what are the forces acting on the body? Who's the body? I'm the body. Trust me. When the doctor tells me to go lose weight, he's saying, your body needs to lose weight. Now I have a surprise for him. So, what are the forces on the body? Gravity and normal force. Anything else? No. So we write Newton's second law. Newton's second law says net F equals ma. And technically, you write Newton's second law in every direction for which this applies. In other words, if I'm being pushed over that way with the scale, you would have to write Newton's second law in the x direction and Newton's second law in the y direction. We'll see this in a little bit. So now what? Now we write the left side Newton's second law based on the free body diagram. What do we have? Equals. And the question is, what's my acceleration? And the acceleration, 0. I'm not going anywhere. Not only am I not going anywhere, I'm definitely not accelerating anywhere. So that's 0. And so what does Fn give me? Fg, which is mg. In other words, normal force tells me my weight. That's right. Stand on a flat surface, step on a scale, and it tells you your weight. Although you'll see that's going to change depending upon where you are on the surface of the Earth. Next, what do? What's the next thing I have to do? I take my trusty scale. I go to an elevator. So I go into an elevator. Here's the elevator. Here's Khalil. He all of a sudden turned blue. And it's not out of embarrassment or due to choking. Free body diagram. What do we got? Gravity. What else? Normal force. Anything else? Is there any other forces? Is there an applied force on me? Is there an applied force on me? In other words, what are the forces that I'm feeling in that elevator? What do I feel? I feel gravity pulling me down, and I feel the scale pushing up. Do I feel anything else? No, those are only forces on me. So, I write Newton's second law. And this is accelerating upwards, right? So that means acceleration's going up. And what are we calling up? Positive. So A is, meaning it's greater than 0. Okay? We write Newton's second law. What's on the left side? The free body diagrams. What do we get? We get, can't hear you, Fn plus negative Fg equals ma. So therefore, Fn is equal to Fg plus ma, which is equal to mg plus ma, which is equal to m times g plus a. And notice, what is that going to be greater than? Well, obviously. What is it definitely going to be greater than? mg. In other words, I take this onto an elevator that's accelerating upwards. What do I feel? I feel, well, I look down at the scale, and all of a sudden it went from 250 to 260, and I say, oh. Yes? Well, what I'm doing here is I'm factoring out the m. Right? These two share an m, factor it out, you have g plus a. Now what? So I accelerate downwards. So, here, same elevator. Same Wednesday, October 7th, 2015. Okay, so now I'm accelerating downwards. So what does that mean? That means A is less than 0. Does this free body diagram change? No, I still feel the same forces on me. So it's Fn, it's Fg, right? And so I write out Newton's second law. I have Fn plus negative Fg equals Ma. Fn equals Fg plus Ma equals Mg plus Ma equals M times G plus A. What is this less than? It's less than Mg. So what do? Take out my phone, I take a snapshot, I send it to my doctor. I say, voila, I lost weight. Aren't you proud? Andrew says, I've had enough of this conversation, Mr. Khalil. I've had enough of answering all these questions in class. In fact, I've had enough of you questioning me, period. So what does he do? Takes out a pair of scissors. And he cuts the cord. And of course, since I teach physics, what do? First thing I do is, that's right, I look down at the scale. And I ask myself, what does the scale say? And what will the scale say? Look at it. Tell me, what would this scale say? Look at it. What is my acceleration?
Would the scale say 0?
The scale says 0. Because all of a sudden, A equals what? What does A equal when he cuts that cable? What does it equal? What does it equal?
Gravity.
Wait, no. Be very careful. What are we calling up? Positive. So, I'm accelerating down at magnitude of g, so the acceleration is negative what? Negative g. I look down at the scale, and it reads m times g plus negative g, which is 0. In other words, what do I feel? There's a term for this. I feel weightless. I feel weightless. This is called apparent weightlessness. And this is what anyone who's in free fall feels. They feel like they're weightless. You go, you jump out of a plane. This is what you feel. You go on the space station. You put a scale underneath your feet. Guess what the scale says? 0. Questions? Kilimanjaro! What is this?
Remember Kilimanjaro?
No!
How could you not remember Kilimanjaro?
Because I didn't. Oh, Kilimanjaro, of course!
Come on, Mr. Khalil.
The drop of doom. That's exactly what you feel. That's exactly what you feel. So, any questions? No questions? You sure? So notice, I'm showing you the process of actually solving physics problems. If you're looking for a formula here, you're looking in the wrong place, because all I need to do is just slightly modify the problem. The formula's worthless. It's a process that matters. So, now, let's talk a little bit about friction. So there's basically two types of friction. There is static and kinetic. Static and kinetic. Now, one thing that's shared between both of them is that both of them oppose the relative motion of an object and the surface it's on. Notice I said the relative motion of the object and the surface. There's a reason for this. And you'll see there's very subtle things that play out when you actually begin observing friction from this Newtonian perspective. So the easier one to analyze between static and kinetic without question is kinetic. So what is kinetic friction? That's a friction associated with sliding. So I'm going to ask you a question. If you were to guess, what force would the force of friction be proportional to? Well, you say normal force because you did the reading. But what would you guess? Okay, that's kind of interesting. Anyone else? I mean, how many people think the force of friction should be proportional to the weight of an object? Yeah, whatever. See, I mean, think about this. Do you think the amount of friction that the Earth exerts on this desk is greater than the force of friction it exerts on, let's say, this stapler? Yes or no? Do you think that the floor exerts an equal force to both of them? Yes or no? Really? You think the Earth exerts the same force of friction on that stapler as it does on this desk? In other words, it would require me to apply the same force on this desk to move it as that stapler? No. Why would this require more? Yes. Okay, so it has greater mass. So the first inclination is that it's due to the increased weight. That's your first guess. That is due to the weight, yes. Ooh, points of contact is an interesting question. And it's one that we're going to rule out shortly. So, but let's actually look at the whole notion of weight. And the question is, does the force of friction depend on the weight of an object? Yes or no? Please, don't focus on your phones just yet. What do you think? Should it depend on the weight? And if you say no, tell me why. Anyone? Emily, should it depend on the weight? Yes or no? Should the force of friction depend on the weight? Then I'll ask you a question, since you said no. How can I decrease the force of friction that the floor applies on this desk? What would I do to the desk? How would I move this desk to decrease that force of friction? Very good. You'd pick it up. That's exactly correct. And do you need to lift it off the ground in order to decrease friction? No, all you need to do is just apply some force upward. Right? If I apply an upward force, if I try to move this, you can hear that friction. Okay? Now I apply an upward force and try to move it. What do you notice? It's slightly less, right? So what's happening? Free body diagram. You guys tell me what's happening. Okay? So therefore? Friction should be proportional to the correct. So let's take a look at the desk. What are the forces acting on the desk when I lift it up? So gravity, that's the wiffle ball one. So gravity. What else? And there's a reason why I say wiffle ball as opposed to softball, which is what's usually used. And the reason is that if I were to play softball, I'd be crushed. So, you know, I'm terrible at these things. I can't stand moving objects. So, what else? What else? Normal force. Where's the normal force? Applied on the desk. Which direction? Up. So normal force. And what else? The applied force. In which direction is the applied force? Upwards. So we write Newton's second law. What does it say? Spell it out. Spit off all three terms. Fn plus negative g plus equals ma. What's the acceleration in the vertical direction for this thing? Yes. What's the acceleration in the vertical direction for this thing? Is there an acceleration? Do you see that desk accelerating upwards or downwards? The answer is no. That's 0. So therefore, solve for Fn. What do you get? Fn is equal to Fg minus Fa. So notice what happens if Fa equals the weight or slightly greater than the weight. If Fa exceeds the weight, what happens to the normal force? Well, be careful. Wait, be careful. What happens when that normal force is 0? What happens to the normal force when it goes to 0? That means what is happening to what? When Fn is 0, that implies that the ground is doing what? It's losing contact. In other words, the ground no longer exerts a force on the desk. How would you no longer exert a force on the desk? That means that is the threshold for loss of contact. Loss of contact. Can Fn be negative? Yes or no? The answer is absolutely not. You can write negative Fn, but Fn is a number. That force, all your forces are positive numbers. So that's the lowest value Fn can have. Similarly, what's the lowest weight you can have? 0. So if the applied force exceeds the force of gravity, what happens? If it exceeds the weight, what am I doing? I am lifting it and accelerating it. No longer has contact with the floor. Fn goes to 0. As a result, is there any friction that the floor can exert on the table? No. So what does that tell you about the force of friction? It should be proportional to the normal force. But then this tells you something else. This tells you that there's a very bad way to move things. Probably the worst way you can move something is to push down on it.
Mr. Gill, did you break a table?
I hope not.
Can we break a table?
It happens in physics once in a while. So, let me actually demonstrate this. So I'll take this desk. Notice, if I lift up, is it still in contact with the floor? A little bit, right? That means that the applied force is not quite equal to the weight. Okay? Now, notice, am I applying a force upward or downward? What do you hear? You hear the forces of kinetic friction. Right? Now what? I'm going to apply a force downward. That's not really that good of an example. That just tells you that these bottoms have a preferred direction for which they will increase or decrease friction. So, come on! I want to get that maximum sound out of this. All right, the whole point is, when I push down, what's happening to the force of friction? It's increasing dramatically. So that tells you what? Well, what's increasing when I push down? Correct. The force of the Earth on the desk increases. Why must it increase? Correct. Or another way to look at it is this. I'm applying a force downward, correct? Gravity's applying a force downward. Is this thing accelerating downward? No. Therefore, the force that's exerted upward must be equal to the sum of those two. So the more I push down, the greater that sum is. So there you have it. Force of friction is proportional to the normal force. And it's important to actually not just be given a statement, but to actually understand where it comes from. Why it's the normal force versus the weight. Because it's not obvious that this is the case. So how do you take a proportion and make it an inequality? What do you need? Here's a proportion. No. How do I take a proportion and make it into an equality? You guys all took math. You've took many maths. How do you take a proportion and make it into an equality? What do you need? You need something called a constant. And that constant is mu. So that is the constant of proportionality that turns that proportion into an equality. That's called the coefficient of kinetic friction. And the coefficient of kinetic friction depends on an object and the surface. In other words, you can't talk about a surface having a coefficient. In other words, asphalt, right, what we drive our cars on, does not itself have a coefficient of kinetic friction. What you can talk about is the coefficient of kinetic friction between rubber and asphalt, between wood and asphalt, between steel and asphalt. Now, will all these coefficients be the same, yes or no? No. Depends upon how materials interact. And so now Gabby had an interesting claim, or an interesting question about friction. She asked, does friction depend on the amount of points of contact? And it's a very interesting question. And so, to illustrate this, take a look at this board, and everybody should get up and look at it. What do you notice about this board as I'm about to slide this thing? As I slide this thing, what do you notice? Take a close look. There's less and less points of contact. So let's weigh this thing down. So what do I use to weigh this down? How about I use, I don't know. Come on now. Come on, guys.
Use that speaker.
Those weights.
Let me see if this will work. This might be too massive. So, does that work right? No, wait, is that 0? Yeah, that's 0. Okay, so now, what do you notice? You notice it just fell off. That's at 0, right? So, what do you notice? I mean, I don't even think this illustrates this well. Let me get another scale. Chop. All right, this should work. So, take this. Notice it stays the same. So you go to a dealership, right? And you go buy a car. And the car salesman says, all right, we have 2 different types of race cars. One with thick tires, one with thin tires, right? And you want to be safe, so you want the maximum, theoretically you would want the maximum amount of surface area of contact with the road, right? And the answer is? No, it doesn't matter. But guess what? The answer is, it matters. So, in other words, what you're seeing here is a very simplified view of friction. And the reason is because this is not deforming. This mass, this surface is not deforming. When a surface deforms, like a tire would, right? What does it mean to deform? Change shape, right? So it's going to change shape based on the road, based upon the mass in the vehicle, etc. When it deforms, all bets are off. So generally you want the thicker tired car. So, but for our purposes, it's independent of the points of contact because these are non-deformable objects. Now, I want you to notice something here. This is something that's actually quite interesting because we're done with kinetic friction now. We're totally done with kinetic friction, at least on a theoretical level. Now let's talk about static friction. So, first thing I want you to notice about static friction is what happens. I'm applying how much force right here? 6 newtons. What's the force of static friction? 6 newtons is correct, right? What? Wait, all right?
No, I think so, but...
Okay. Let's suppose it was greater. How can you rule out the fact that it's greater? Can the force of static friction be greater than the 7 or 8 newtons I'm applying? Yes or no? Why? Why can't it be greater? Yes. It would be accelerating that way. If the force of static friction exceeded the applied force, it would accelerate. You'd observe it accelerate that way. And if you do observe that, you should run. I mean it. Seriously. You observe something like that, you run. Because all hell's about to break loose. Okay? So, I go and I increase the applied force to 10 newtons. What do you notice? Still staying there. What does that mean? That means the force of static friction is 10 newtons. So I increase it to 11 newtons. What do you notice? Still there. I increase it to 14 newtons. 14 newtons. What do you notice? I increase it to 15 newtons. 16. Ah! Notice what happened. At about 17 newtons, it breaks. So the maximum force of static friction was 17 or 16 newtons. So let's actually see if we can actually mathematically describe this. So the applied force, we'd say that the applied force must be, how do we write this? That it's going to be less than the maximum force of static friction. Right? That's FFS max. Okay? And this is going to be true so long as the object, what? That's right, doesn't move. Object at rest. Okay? So, just want to make sure that this is, so this is less than FFS max. Now, what can we say about the force of static friction? That's equal to the applied force, so long as the object's at rest, right? And as long as the applied force is less than the maximum static friction. And so that's basically the most you can say. All right, so now, notice this is just the force of static friction. This isn't the maximum. So now, let's actually look at the maximum force of static friction. What can we say about it? Well, immediately after it breaks, what takes over? Kinetic friction, right? So we know that just like it has all the same properties of kinetic friction, namely it should be proportional to what force? That's right. So the force, the maximum force of static friction should be proportional to the normal force. So to make this an equality, what do? Add a constant. So what is that constant? FFS max is equal to mu s Fn, where mu s is the coefficient of static friction. And now the question is, how does mu s compare to mu k? What do you think? Well, what do you observe when an object breaks static friction? Mu s is greater. Why?
Because when that starts moving, the force is much lower when it breaks.
That's correct. That's exactly correct. Immediately when it breaks, so watch what happens as I increase the force. When it breaks, what do you notice? It drops down dramatically. So what that's telling you is that, well, first off, notice it accelerates immediately, right? That's a telltale sign that there's a drop in the force of friction. So, and notice, what do I have to do to move it at a constant velocity? I have to. What do I do to move this at a constant velocity once I break static friction? I pull it, but at a, look at that force meter, at a weaker constant force, right? So I decrease the applied force. Well, the only opposing force is the force of friction. So what that tells you then is that the force of kinetic friction is less than the maximum force of static friction. Well, since both of them are proportional to Fn, that tells you that the coefficient of static friction is greater than or equal to the coefficient of kinetic friction. Any questions? No questions. Really? You guys are incredible. You guys are superstars. You're amazing. All right, so now we've got like a half hour left. Yes?
Could MS and MK be equal?
It's mu-s and mu-k. When can they be equal? I don't know. It would basically have to be some type of specialized combination of materials such that the force of static friction is equal to the force of kinetic friction. Pretty unusual, though. It's almost always greater. In other words, it's always easier to keep an object in motion than it is to start it. Well, that is because it's harder to break static friction in almost all surfaces than it is to keep it moving or to continue to break kinetic friction. So I guess the last thing I should probably do is a friction problem. So let's actually look at how this works. You guys can have a seat now. You're going to go into your lab very shortly. Yeah, if you want, I mean, I'd be curious to actually have a standing class, just so you guys actually have some time to stretch. So what I want to do is I want to figure out what the coefficient of static friction is, coefficient of kinetic friction between a crate and the flatbed of a truck. So what does that mean? You have some truck. Actually, no. Let's not even do that. No truck. Suppose you have a block. And you give the block a push, right? And when it leaves your hand with a velocity v. It's going to the right. And the question is, after it goes some displacement, delta x, say delta x, and it comes to rest, find the coefficient of kinetic friction. So in other words, some time later, it's at rest, some delta x away. Find the coefficient of kinetic friction. What do you do? Well, it's a physics problem. First thing you do is free body diagram. That's right. So you're getting the hang of this. Notice before I said coordinate system. Now I say free body diagram. What are the forces acting on this block? Spit them out. Gravity. What else? What else? Friction. So gravity. Normal force. Friction. What type of friction? Kinetic friction. Any other forces? Is there an applied force once it leaves my hand? Nope. No other applied force. So, let's look at this kinematically. Kinematically, what do we have? We're solving for mu k. That's what we want. From the standpoint of kinematics, what's its final velocity? 0. What's its initial velocity? V. So we have Vf equals 0, Vi equals V. So we have, second kinematic equation says Vf squared minus Vi squared is equal to 2 times A times delta x, correct? And where's this thing accelerating? Which direction? Which direction? Meaning horizontally. So we'll call this the positive x. We'll call up the positive y. So I can even be more specific and say this is ax, meaning it's the acceleration in the x direction. So we replace the variables. We have v squared is equal to 2 ax times delta x. Now what? Now we need to solve for a. How do we solve for a? Newton's second law. Well, let me zoom in. Go to like 150. Let's go to 100. All right. So how many directions do we have in this problem? Directions. Yes. Yeah, sorry. Thank you. Good catch. So, how many directions do you have? You have two. You have the x direction, and you have the y direction. We write Newton's second law in each direction. Net force in the y equals MAY. Net force in the x equals MAX. Which one do you want to do first? Let's do the y direction. In the y direction, let me actually grab this. Get over here. Okay? What are the forces in the y direction? I can't hear you. So we have Fn minus Fg equals MAY. But what's AY? 0. This thing's not accelerating vertically. So that's 0, which tells you that the normal force is equal to Fg, which equals mg. Then, what do? Do the x direction. What's the net force in the x direction? I can. Say it like you mean it.
Negative FFK.
That's right. Negative FFK. Why is it negative? Very good. It's going to the left. It really is. And that's equal to MAX. But what is FFK equal to? The force of kinetic friction is equal to times Fn. But Fn is equal to?
FG.
That's right. So this equals mu mg. And so, now I zoom to 75. And you have negative mu mg equals max. Therefore, ax equals what is it equal? We're solving for the acceleration in the x direction. So ax equals negative mu g. Notice the acceleration is independent of what? What is the acceleration independent of? I can't hear you. What? Very good. Acceleration is independent of the mass. It doesn't depend on the mass. So now we plug this into right here. We have negative v squared is equal to 2 times negative mu g times delta x. What are we solving for? Mu. To solve for mu, you divide it by everything else. You get negative v squared over negative 2 g delta x. Equals mu k. And mu equals v squared over 2g delta x. Any questions? Yes. Oh, sorry. Any questions? Notice, yes.
How did you get that negative FK equals mu?
Okay. This is very important. So, because what you're getting is like your first real taste of everything coming together. From the vertical direction, we get that Fn equals Fg equals mg, because Fg is the weight, weight's mg. So therefore, the normal force is mg. But the force of kinetic friction, we established earlier, is proportional to the normal force. It's proportional to the force that the ground exerts on this block. So to write that out, you say FFK, the force of kinetic friction, is equal to some constant, mu k, times Fn. But Fn equaled mg. So therefore, Ff is equal to mu mg. And the reason it was negative is because the force of friction is directed to the left. Questions? This is the time to ask, because this embodies the spirit of what we're going to be doing for a while. And notice, are there numbers? Maybe in some of your baby problems there are numbers, but do the algebra first. Do the algebra first. Notice, you wouldn't notice that the acceleration was independent of the mass if we had numbers. You have to look at it algebraically to understand that. All right. So now this would be a good time for you guys to start your lab. You're not going to be able to finish it in this block. You'll have tomorrow as well. Did everybody take one of these? Lucky for you, the last class already set it up. And for lab partners, what I want to do is I want to shuffle up the mix. So, actually, do you want to shuffle up the mix or you want to keep your lab groups? You sure? Have a blast.